Hey everyone, welcome back to the series of Mastering Digital Logic Design with Logisim. In the last video, we have talked about the basic components of the CPU, the ALU, control unit, registers and memory, and how they all fit together to form a functioning processor. We also touched on the RISC-V instruction set architecture and how it's simplified yet powerful framework used in modern processors. Now that we have got a good grasp on the overall structure, it's time to dig deeper into one of the most critical components of our processor, which is the control unit. In today's video, we will design and implement the control unit for our RISC-V Single Cycle Core. The control unit is the brain of the processor. Its job is to decode instructions and generate the control signal that direct the operation of the other components, like the ALU, the register file and the memory. Without the control unit, the CPU wouldn't know what to do with the instructions it receives. In this video, we will walk through how to build the control unit step by step. By the end you will have a fully functioning control unit capable of decoding RISC-V instructions and orchestrating the entire CPU. Before we dive into the design process, let's take a moment to review the structure of a RISC-V instruction. RISC-V instructions are 32-bit long and include several key fields that dictate the operation the CPU will perform. First, we have the opcode, which determines the type of operation such as arithmetic, load, store or control. Then there are registers field which specify the source and destination registers involved in the operation. Lastly, we have function codes called function 3 and function 7, which further refine the type of operation, whether it's an addition, subtraction or a logical function. One of the advantages of RISC-V is highly regular instruction structure. This consistency simplifies both hardware design and the process of decoding instructions. Once you understand how to read these fields, you can easily interpret what the CPU is being instructed to do. Let's break down an example. The instruction we have here is of add x1, x2, x3. In this case, the opcode, which is 0110011, which tells the CPU it's an arithmetic operation. The RD field or the destination register is x1, where the result will be stored. The function 3 field is 000, indicating an addition operation. The two source registers are RS1 and RS2, which are x2 and x3 respectively. Finally, the function 7 field is all 0, further specifying that this is a regular addition. By breaking down the instruction like this, we can clearly see what the CPU is being asked to do. Add the values in x2 and x3 and store the result in x1. Now, RISC-V Single Cycle Core actually has two types of control units, the main control unit and the ALU control unit. Each of them plays a distinct but complementary role in controlling the CPU. The main control unit is responsible for decoding the instructions opcode and generating the high-level control signals. These signals determine how the processor will handle things like accessing memory, writing to registers, and selecting ALU operations. Think of the main control unit as the executive director. It gives the general direction that guides the entire CPU. Then we have the ALU control unit, which works closely with the ALU. The ALU control unit takes input from the main control unit, specifically the ALUOp signals, and use those along with the function codes from the instruction to tell the ALU what operation to perform, whether it's an addition, subtraction, bitwise AND or any other operation. In short, the main control unit manages the overall control signals for the processor, while the ALU control is dedicated to ensuring the ALU perform the right arithmetic or logical operation. Both control units need to work together seamlessly to make sure the processor executes instructions correctly. With that overview in mind, let's now get into designing the main control unit. Let's break down the control signals generated by the main control unit. Each signal plays a crucial role in directing the operation of the processor, and understanding them is a key to our design. First up is RegWrite. The signal enables writing data back to the register file. If the instruction requires the CPU to store a result in a register, this signal will be activated, allowing the register to be updated with new data. Next, we have immediate source. This control signal determines the source of the immediate value that the ALU uses. Depending on the instruction type, immediate source tells the processor where to retrieve the immediate data, either from a specific part of the instruction itself or from a register. Moving on to ALU source. This signal selects the second operand for the ALU. If ALU source is high, the ALU will use an immediate value, a constant embedded in the instruction, as its second input. If it's low, the ALU takes the value from another register. This flexibility is vital for handling various instruction types. Next, we have MemWrite. This signal tells the CPU whether it should write data to memory. When MemWrite is activated, the CPU takes the data from the register file and writes it to the specified memory location, which is crucial for stored instructions. Now, let's look at result source. This signal selects the source of the result to be written back to the register file. If the result source is high, the data returned to the registers come from memory. If it's low, the data comes directly from the ALU. This is crucial for ensuring that the correct result is stored after operations. Now let's discuss branch. This signal informs the CPU whether a branch instruction is being executed. If branch is high, it means the next instruction will depend on the result of a comparison, allowing the CPU to jump to a different instruction in the program based on conditional logic. Finally, there's ALUOp. This signal specifies which operation the ALU should perform. It provides information about the type of arithmetic or logical operation needed, guiding the ALU in executing instructions such as addition, subtraction, or bitwise operations. As you can see in this truth table, each opcode corresponds to specific values for the control signals. For example, for an R-type instruction, RegWrite is activated to store the result in the register file, while the MemWrite is set to low, indicating no memory operations are taking place. On the other hand, for the load instruction, result source is high, meaning the data written to the registers come from the memory. To sum it up, these control signals, RegWrite, immediate source, ALU source, branch, MemWrite, result source, and ALUOp are essential for managing the flow of data and operations within the CPU. Our goal is to design the main control unit so that it generates the correct signal based on the opcode of the instruction being executed. Don't have to worry about this. You will understand this in much detail when we move towards the further lectures, where we will using all these signals into our actual design, so you will get the better idea. But for now, you just have to know what these control signals are and what are the main purpose for mentioning it in the truth table. Now, let's hop over towards the Logisim and start building our main control unit. This is a crucial component that decodes the 7-bit opcode from the instruction and generates the appropriate control signals necessary for executing that instruction. Now, there are multiple ways you can design this control unit. You can either use a decoder, comparators, logic gates, multiplexers, and as much as you want. There are multiple you can say approaches available, but the approach we are going to use is very much simple. We are going to use comparators, multiplexers, and gates to design this main control unit. So first, initially I am going to get the comparator here. We can get the comparator from the arithmetic tab, and I am going to place into our canvas. Here I am going to get 4 comparators. The reason I am getting the 4 comparators here because we are now designing the control unit for 4 instructions, which is the load, store, R-type, and branch, right? So I am going to connect a input here which will be act as our opcode. As we know, the opcode is of 7 bits, so let's change this data bit from 1 to 7. And I am going to connect this opcode to the one of the inputs of each comparator. Right? Now you can see we are getting an incompatible bits error. So first change the bit of the comparator from 8 bits to 7 bits. Okay, so once we are done, here you can see all the errors have been removed. Now the second input of all of these comparators, I am going to use a constant value here. The reason I am using a constant value is because we are using the opcode directly rather than using its binary value, right? So you can see the constant values bit is 1 bit, so we have to change data bit from you can say from 1 to 7 to match the compatibility. And we can connect it with all of these comparators for now, right? Here. Now we have to place a constant values here. So you can, let's get back to the truth table. Here you can see the load word have a constant opcode of all 0, 1, 1, which makes it a binary value of 0, 3, or in hexadecimal you can say it makes a 0, 3 value. So what we are going to do, we are going to change this constant to 0, 3. So here we are just comparing our input opcode with 0, 3, and if the input get matched, so we will going to get a high result on equality. Now the second input is of store word, which is 0, 1, 0, 0, 0, 1, 1, which makes it a constant value of 2, 3. You can easily say it's 23 also. So now I'm going to change it to 23. Again, if we see here, the R-type opcode is 0, 1, 1, 0, 0, 1, 1. So it makes an opcode of 3, 3. Right? Now let's move towards the branch equal. You can see here it's the opcode value is 1, 1, 0, 0, 0, 1, 1, which makes it a value of 6, 3. So we are just going to make this constant 6, 3. Right? Now this will just going to check that incoming opcode is equals to these values or not. We are getting using comparator for each different value, so we are going to get 4 high signals here. So now we are going to use a multiplexer here. I am going to connect a multiplexer here for each comparator here. So but before we get add, let's make a logic for one. First let's change this data bit from you can say from 1 to 7 and just disable the include signal here. So I am going to connect this equal sign which is getting answer of my comparator with the select bit of the mux. It will trigger this mux only when my input opcode is equals to 0, 3. So one of the input of my mux will be, you can say, will be 0, right? And the second input of my mux will be 0, 1. You can say right here, using this mux to select my control signal for our next logic I'm going to design here. So either it will going to select the 0 input, or it will going to select the 1 input, right? So just let's make its multiple copies here for each and every comparator. Right, now I'm going to connect this equal sign to the second mux, this equal sign to the third mux, and this equal sign to the fourth mux. The one input for each mux will be same, which will be 0, right? So we are just going to change the second input. So you can say that first input of each mux is 0. The second input of this mux will be this will become 0, 2. This will become 0, 3. And this will become 0, 4. You must be wondering why I am doing such input. So let's move forward and you will get the idea. Now here I am just going to connect an OR gate here. You can select the OR gate from the gate tab, and first let's change this number of inputs from 5 to 4. Okay, I'm going to use a 4 input here, and I'm going to connect this mux outputs to each of this OR gate. Okay, so the main reason is that I want this output of the OR gate if either of the input is 1. Okay, at the moment I'm getting an opcode of 3, so this comparator will be activated and it will going to select a high signal at equal sign, which will going to operate this mux. And if the value is 1, so I will be getting a 1 output at the mux side, and which will be getting OR with all of these zeros, because at the moment only one mux will be enabled. So all these mux will be putting an output of 0 here. So when I'm going to OR this 0, 1 with all 0, so I'm going to have a output of 0, 1. Same, you can see the logic will be applied for the second mux, when 0 for all of the other mux will be providing 0, and the output I'm getting of 0, 2. So when I'm going to OR these signal together, so I will be getting the output of 0, 2, and so forth, right? This will be the basic example which you are trying. I'm trying to explain to you. Okay, here you can see we are getting an error of incompatible bits. So let's change the bit of the OR gate to 127 for now, right? Okay, I'm just going to select all of these signals so I can drag them down. Okay, let's place it here, bring this opcode here. Okay, so I can just move it. Okay, let's keep it here. Now we are going to use this OR gate output as an input to another mux. Okay, now think of this like that I'm just using this opcode for the comparator. When the comparator gives me results, I'm going to use this 1, 2, 3, 4, which will act as a select line signal for my another mux. So I'm just going to place here a multiplexer here. Okay, and just disable this enable first. And so we are going to connect this with this select line here. Now currently we are facing using 4 instructions at the moment, right? The load word, the store word, the R type, and BEQ. So I'm going to use the change the mux from 2 by 1 to 4 by 1. So to do that, we know that we have to change its select bits from 1 to 2. So now here you can see I am getting the 4 input values and 1 output value. So we have to make this compatible. I have to change this OR gate bits from 7 to 2 here, and also this mux signals data bits from 7 to 2, right? Now I have to change the value of constant here also from 7 bit to 2 bit. 7 bit to 2 bit. There is sorry for the delay, but I think it's better so that you know why I'm changing this bit. So I have to make everything and each signal compatible with our logic we are designing. Either you can design your logic first and then start designing in the Logisim, or you can do it either ways, right? Okay, here you can see the reason I cannot write the 4 here, because of the data bits. The 2 bits only represent 0, 1, 2 and 3. So I guess we have to change it to 3 here, right? So, and we are going to change this mux select line for 2 to 3 for now. Okay, and the data bits of this mux will be of 7 bits. You must be saying why we are using such a long mux. So let's just because we are planning, we can implement further instruction or extend it further for future instructions as well. So you can use it for making it 3 select bits here and the data bits of 7, right? So now, to make things a little bit of easy, either I can make a logic for each signal bits here, or for each signal, for example for the RegWrite, for the MemWrite, or for all of that, or either we can just say what we have, can just connect the 7 bits input to these muxes and we can write the value directly. Here you can say let's say what value I was having for the load word instruction. I've placed the opcode at the first comparator, so if once I get, I'm going to collect that 1 bit. Okay, so you can say that I am going to write all of these values as a bit here. So I'm going to write 1 0 0 1 0 1 0 all 0, right? So I have was 1 at most MSB, then I have 2 0, then I have 1 and 0 1. So let's write 1 0 0 1 first. Okay, I'm going to change this. Okay, so we are not going to connect this select control signal here, and let's make it of 7 bits, right? So you can just if we can easily convert this value into some decimal format, so you can count it as hexadecimal here. You can say this is a 8. Okay, this will make a value of 2, so it makes 128. So I can write it 120. We are done with our design. Here right now I'm using the input pins here to toggle the inputs to show you the working, but you can use a constant value here and place the direct value which are you will be getting from the control signals, right? So let's just simulate this, and first let's just toggle all of these values. So here you can see I have 1 0 0 1, so 1 0 0 1 0 1. Okay, you can see here this is the one signal, and if we move towards the second one is 0 0 1. Okay, see here we have done a small mistakes. You can see the data bits of the mux should not be 7, it should be like 1 2 3 4 5 6 7 8 and 9, right? So it should be of 9 bits. So let's just change its data bits from 7 to 9. Right, so just let's place a constant here. Okay, let's change this constant bin to, I guess, to 9. So let's change this bit. First we have the 128. For second we have, you can count as like 0 7. So 0 7 0, I can write it as 0 7 0 for now. Okay, for third I'm going to have 1 0, which makes a 2 2 0, so 1 0 2. I'm going to write it as 1 0 2. And here you can see it's base of 0 1 0 1, which makes a 5 5 8 to 0 85, right? So 0 8 5. Okay, change this output from 7 to 9 bits here. I think we are good to go. Okay, so let's just simulate it. Here you can see we have all the values here. Currently we are not getting any output because our opcode is 0, is not getting compared to any of the values, so we are just getting 0 output from all the muxes, and we are just selecting the 0 mux value, which is all 0. So let's change it to opcode to 3 here. So you can see as soon as I change the opcode to 3, my first comparator gets the result of high and selects the mux output of input of 1, and which getting OR with all of the result of the mux. And here you can see it is selecting the first input, which is 128. So you can see the values here in our output side, which is basically the control signals I am talking about, right? Second, if we make it 2 3, right, so just 2 3 here, you can see the second comparator is getting high and we are getting an output of 0 7 0 here. If we make it 3 3, the third mux gets high and we are getting of 102 output here, right? And if we get make it the value which is the third 63, so 63 will going to initiate the fourth mux, and I'm getting the output of 4 from mux side, and the mux is selecting the 48085 output here to the control side. So this is how our main decoder works, or you can say our main control unit works, right? So there you have it. We have successfully designed a main control unit using comparators and multiplexers to handle control signal for a RISC-V Single Cycle Core. This design is both flexible and effective for interpreting instructions, right? So now let's move towards the second part. Now that we have designed our main control unit, it's time to delve into the ALU control unit. The ALU control unit takes specific inputs to determine the operation that the ALU should perform. To do this effectively, we need a truth table that maps the input to the appropriate ALU operation. First, let's take a look at the ALUOp signal. The signal is crucial because it defines the type of operation we want to execute. 0 0 corresponds to load and store operation. 0 1 indicates a branch operation, specifically BEQ, and 1 0 is used for ALU operations. The function 3 field is a 3-bit code found in the instruction that specified the exact ALU operation within the R-type instructions. The ALU can perform multiple operations depending on the function 3 value. However, for operation like addition and subtraction, the ALU needs additional information because you can see the function 3 value here is exactly the same. When the ALUOp is 1 0 and the function 3 value is same for both addition and subtraction, which is 0 0 0 respectively, we utilize the OP bit 5 and the function 7 bit, also the 5th bit, to differentiate between the two. This ensures that we accurately select the required operation, right? Here you can see when the ALUOp is 0 0 and the function 3 is all 0, so either the opcode and function 7 bit combining together make a combination of 0 0, 0 1 or 1 0. We are going to generate a control signal of all 0, which is going to perform a add operation. If the ALUOp is 1 0 and function 3 is all 0, and if the combination of 5th bit and function 7 5th bit makes a combination of 1 1, so we are going to generate a control signal of 0 0 1, which is going to perform a subtraction. If the ALUOp is 1 0 and function 3 is 0 1 0, so we are going to perform an operation of set less than by generating a control signal of 1 0 1. Same if ALUOp is 1 0 and function 3 is 1 1 0, so we are going to generate a control signal of 0 1 1, which will going to perform an OR operation. If the ALUOp is 1 0 and the function 3 is all 1, so we are going to generate an ALU control signal of 0 1 0, which is going to perform an AND operation. Like this, we can add multiple fields here of function 3, which will going to execute many other operations of the ALU. Here you can see that when the ALUOp is 0 0, we are not checking the function 3 and opcode bits here. We are just generating an ALU control signal of all zeros, because we know that we want to perform an or add operation for load and store instructions. If the ALUOp is 0 1, so again we are just generating a control signal of 0 0 1, which makes sure we are performing a subtraction for our branch instruction. Now this truth table is fundamental for our ALU control unit design, and it helps map specific inputs to the correct ALU operation. By implementing this logic into our control unit, we ensure that the ALU executes the appropriate operation for any given instructions. With our truth table defined, we can now move forward and implement the ALU control unit in Logisim. Let's see how we can wire this up and create the necessary logic gates and multiplexers to facilitate these operations. Okay, so before we start designing of the ALU control unit, I'm just going to here and make a new file of Logisim here, and so that we can have a separate design here of the main control and the ALU control, so we are not mixing up all the things here. So first just we are going to select a constant value here, I can say of from here you can get the constant value. Okay, I'm placing it here, and then we are going to use a comparators here as well. So just drag the comparator here, and the one bit of the comparator will be connected with the a constant. Now you know the ALUOp is of 2 bits, right? So just change it with our input pin because it's an input here. So I'm changing its input data bits from 1 to 2. So we have to change this comparator from 8 bit to 2 as well, and I'm going to use the constant here to compare it with our ALU opcode. The first opcode which I'm going to use is of 0, right? So I'm just checking if my ALUOp is 0 and the constant value is also 0, so if both are 0, so that makes sense. Let's change this constant bit from 1 to 2. Again, let's place another comparator here, and I'm going to connect the ALU opcode here. The second input will be a constant value, which will be going to be 1, right? I'm not just placing the constant value directly. You can see we have the ALU of values here from the truth table. First we have placed 0, now we have placed the 1, right? Okay, and now I'm going to place a third comparator here and connecting its input with our ALUOp, and here I'm going to make a constant of 2. Okay, just dragging it down a little bit so we can have a larger space. Okay, so this is the first one of the first chunk of the logic we are designing here. So what I'm going to do is I'm going to again use some multiplexers here to select signals from here. So let's just add the multiplexers from multiplexer tab. Alright, okay, so just disable this for now, this enable signal, and I'm going to connect this equal to sign with here, right? And just using another multiplexer here, connecting is okay. I'm not changing the data bits here right now so that we can change it afterwards, so we don't have to change it again and again. So this is our logic here, and now what I'm going to do is I'm going to OR all of these 3 muxes, because for the current moment I just want the ALUOp, either it can be maybe 0, it may be 1, or it may be 2, right? So we are just going to use a OR gate here again, changing its number of inputs from 5 to 3, and connecting this mux output. Okay, connecting this mux output and connecting this mux output. So from here you can see that we have designed the logic of the very first chunk, that if the ALUOp is 0 0, okay, compare this with the 0 value. If it be 0 1, so compare it with this comparator. If 0 2, so compare this with comparator. So now I have to again going to use this mux to generate the mux control signals for the second mux, which we are going to use here to generate the ALU control signals, right? So let's just place the first mux here so that it can make it makes things a little bit of clear in our mind. As we know, the output of the mux is a 3-bit ALU control signal, right? So we know the data bits here should be 3, okay, but the control values which I am getting may be different, because here you can see we have the possible combinations of 0 1, you can say 2 3 and 5. So there are 5 possible values. So what I'm going to change, that I'm going to change this in select line from 2 3, so I can use a bigger mux here, and I'm going to this OR signal with the mux select line. So you see the compatible issues, so I'm going to change this OR data bits. Okay, where the data bit? Okay, data bits from 1 to 3. Here you can see we have to change the mux input again, database to 3 as well. Now I have to going to use this constant value here to connect the with mux inputs. Okay, just change this constant values to 3 as well. So first one will be 0. Now I know that for I will be going this 0, right? Because if the opcode is 0 0, so I want to generate a mux control signal of 0, so I'm going to use this 0 position, which will be providing my control signal. Okay, second we are just going to use this constant value to connect it with this mux and this. Okay, so if we are getting an opcode of 0 1, so it makes it of a branch, so I'm changing it to okay, we are just going to connect this one here, right? The third mux will again have a 0 input here, but the second input of the mux is yet to be defined, because we know that if the ALU opcode is 1 0, so we have multiple conditions which we have to check before we decide which of the signal which should be occurring here, so which will be act as a control or select line signal for our mux, right? Before I am just as we have changed the data bits of mux to 3, so I'm going to connect an output pin here. Okay, so change this data bits to 3, and we are just using the control signal constant values here again. At the 0 I will be placing a constant value of 0, right? At 1 position I will be placing a control signal of 1, because we know that it's 1, right? In second position you can say if I am generating a control signal of 0, you can say 0, so 0 position, 1 position and the second position, so here I will be saving a 5. So 5 is basically a control signal of set less than, right? So I'm going to generate this signal. Then we have this value here. I'm just going to make this 5 to value of 3. Okay, I'm not just putting it randomly, I'm getting it from a truth table eventually and making it a value of 2. Here we are going to connect the rest of the input to the default value of 0, right? Okay, I'm trying to make the design as much as clear I can possible. Okay, here we go. So we are done with our design. So just if you first we just walk through it, you can say if the opcode is 0 0 and it get compared with our 0 value, so we are going to get an output of 0 from this mux, which will going to get OR with all of these signals, and the mux will generate, this OR gate will generate an output of 0, which will going to select the 0 input of this mux, so we will be getting a control signal of all 0, which will be going to perform an add operation, right? If we get an opcode of 1, it will going to compare with this comparator, going to produce an output of 2. We are going to get an output at mux side of 1, which will get all with all of the inputs of mux. We're going to generate an output of 1 again. So the mux input 1 will be selected for the output, so it will going to generate a control signal of 0 0 1, and you can go forward like that, right? So this is the design. I'm not completing the design. The second part of the design I am going to left it for you, so you have to practice it for yourself and you have to come with that logic, how you can design that logic, right? So first we are just going to simulate this logic here to see that either we are getting the correct for the first two combinations which you have designed, right? Here you can see the when my ALUOp is 0 0, mux is 0 and output is 0. Let's change this to 0 1. You can see the second comparator gets high when mux is getting an output of 1 here, is getting OR, and you can see that I'm getting a 1 here, right? If I make it a value of 3, nothing happens because it's getting a default value. If I make it a value of 2, now you can see that all of these signals become red. Why? Because we have not provided a second true input here of the mux, right? So that's why it's not just getting any value here, so it will be getting a, you can say here it shows that all E, which is an undefined value. So just to test it out, what if I just place this a constant value of 2 here, right? So what do you think what will be happening here if I change this to 2 and we just simulate it again? So you can see here that the red lines have been gone black again, that simulation is working correctly. I may be getting an output of 2 here from the mux side, which is getting OR with all these 2 inputs. So the OR output will be of 2. So you can see the output at the control mux side is 1 0 1, so which is the second input of the mux. So you can just not place the 2 directly here because we need to make logic for these all 3 inputs, which is 5 3 and 2. Or you can simply say we have to come up with this logic of all of these remaining control signals which we have mentioned in the truth table. So it's up to you to explore it and design it and complete this design on your own. And there you have it. We have successfully designed the ALU control unit for our RISC-V Single Cycle Core by utilizing the ALUOp code signals function 3 and function 7 bits. We can effectively interpret various arithmetic and logical operations including addition, subtraction and logical operations like AND and OR. 9. That's wrap our tutorial. We have successfully designed and tested the two main components of the control unit for our RISC-V Single Cycle Core, the main control unit and the ALU control unit. Together they efficiently decode instructions and generate the necessary signals to keep our CPU operating smoothly. In our next video, we will continue to develop additional components for our single cycle processor. If you found out this tutorial valuable, please give it a thumb up, subscribe to the channel and hit the notification bell to stay updated on our upcoming content. Looking forward to seeing you next time. Till that time, take care and goodbye.